Now, so far, given a joint probability distribution, for example, the probability distribution of x1 all the way to xn, we have looked at how to compute the marginal probability of, for example, the probability of x small n over here, where x small n over here could be any random variable in this joint probability distribution, or the conditional probability of any random variable in the joint probability distribution conditioned upon some evidence nodes that we have observed. And we've seen that this can be easily computed using the sum product algorithm that we saw that it can be done over the undirected graphical model or the directed graphical model, as well as the factor graphs. And in fact, there is another interesting thing that we can infer from the joint probability distribution, and that would be the maximal a posterior problem. And what this means is that given a joint probability distribution of x1 all the way to xn, there are two aspects or two things that I want to infer from this particular joint probability distribution. The first would be, what would be the maximal probability given all the configuration of x1 to xn. Suppose that each one of these random variable xn over here, it's taking some states 1 to k states, for example. There will be altogether k to the power of n combinations of this random variable, and each one of these configuration would give me a certain probability distribution. It will return a certain probability distribution. And here, finding the maximal probability means that I want to find the value over here, which gives me the maximal probability over all the possible combinations of the random variable, the state of the random variable. And of course, the second problem that is closely related to the maximal probability would be to find a configuration that achieves the maximal probability. So we can think of it this way. If I have for example, a two node random variable joint probability distribution, the joint probability distribution, all the probabilities over all the combinations of the state of x1 and x2 can be represented in the z-axis over here, where x1 and x2 are all my random variable, the states of my random variable that you can take. And this probability over x1 and x2 would take some form of the graph. It's actually a surface. It forms a two-dimensional surface over x1, x2. And there would be some configuration here where it will give the maximal probability value of p of x1 and x2. And this would be the combination of x1 and x2, or the configuration of x1 and x2 that gives rise to the maximal probability value of x1 and over x1 and x2. And of course, this might not be the only maximal value in the whole space of the probability of x1 and x2. There could also be a case where there are multiple peaks over here that corresponds to the same maximal value of p x1 and x2. And the maximal a posterior problem, we are asking the question of whether first we can find this maximal value, and second, we will find all the configurations that gives rise to this particular maximal value over x1 and x2. And interestingly, we will see that this can be done using the max product algorithm, which is kind of related to the sum of product algorithm that we saw earlier for inferring the marginal probability as well as the conditional probability. So given a probability distribution of x conditional upon xe over here, where xe are all the observed random variable, the maximum a posterior probability is simply given by the or written as this form over here. I'm going to write the max over x of this conditional probability. So this max over here simply means that I'm after the maximal value of the probability in comparison to argmax over x over here. So this is the value, the probability. This refers to the probability value that is the maxima over all the configuration of x. And this argmax over here simply refers to the configuration of x that gives rise to the maximal probability of this conditional probability over here. So we'll look at the definition of the max value, and to take a max over the conditional probability, we can simply apply the chain rule, which means that this will become the joint probability distribution of x and xe divided by the marginal probability of xe. And since the denominator here is defined over a set of observed random variable, which is not within the x that we wish to maximize over, this means that this term here can be treated as a constant and removed from the maximization step. So we are left with the maximization over x over the joint probability distribution of x and xe, which can be rewritten into p of x multiplied by delta xe xe bar. And this guy over here is nothing but just the marginalization trick that we have seen in the earlier lecture. So we'll represent the joint distribution here with this representation over here, p of x raised to e over here. And this superscript of e simply means that we have incorporated all the evidence into the joint probability distribution of over x. It should be noted that there is a general fallacy of whether we can compute the maximal a posterior problem by just simply solving the marginal probability for each random variable and assignment of each random variable that maximizes its individual marginal. So the answer is actually no, we can't do this. We'll see why is this so. An illustration over here would be this two-node Bayesian network over here, where I have x pointing towards y. So the joint probability distribution of x, y is actually given by p of x multiplied by p of y condition upon x, where the probability of x and conditional probability of y upon x on x would be given as the two probability distribution table here. So the general fallacy over here is that why not we just compute the marginal probability over both p of x and p of y and simply look at the value of the probability over x and y that gives us the maximal probability over the individual marginal probability distribution of x and y. And the max over px and the max over py is not equals to the max over the joint distribution over x and y. We can see that let's compute this marginal probability. The max over x is simply given by this table over here, where we can see that when x equals to 1, it's 0.6. This has the highest probability value over the marginal probability distribution of x. So this marginal probability of y would be marginalization over the joint probability of x and y, and this would be equals to the marginal probability of x multiplied by y condition upon x, where we can simply evaluate this marginalization over x on these two probability tables that we are given. And we'll see that as a result, the marginal probability over y would be given by this table over here. And looking at this table, the maximum probability over y would be 0.4 in this case, at a state where x equals to 1 and y equals to 1. And interestingly, we'll see that the two states over here, as well as the maximal probability of this marginal distribution that we have seen here, it's actually different from the maximal probability over the joint distribution. So if we look at the joint distribution over here, which we can simply compute, so this guy over here, we can simply compute it by taking px multiplied by py condition upon x, and we'll get a 2 by 2 table over x and y over here. And we can see that the maximal probability actually occurs at the state of x equals to 1 and y equals to 2. And this gives a maximal probability value of 0.36. What's interesting here is that the maximal probability, or the state, the configuration of x and y that gives rise to the maximal probability, the joint probability distribution over here, is different from the maximal configuration of the respective marginal probability. So in this case over here, it would be x equals to 1 and y equals to 1. That gives rise to the maximal probability distribution. And in the joint probability distribution, we can see that it's x equals to 1 and y equals to 2 that gives rise to the maximal value. And similarly, the maximal value of the joint probability distribution is different from the maximal value over the marginal probabilities. So what this means is that we cannot compute the marginal probability for each random variable and to find out the maximal a posterior of the joint distribution. We would have to use what is called the max product algorithm. Before we look at the max product algorithm, let's look at the relation between the marginalization to the max operator. So we can see that in the marginalization algorithm that we have seen earlier in the sum product algorithm, the distributive law is made use of on the multiplication over addition. Suppose that I have a multiplied by b1 plus a multiplied by b2 and so on and so forth until I have a multiplied by bn. This is simply equivalent to factorizing out all the a over the sum of all the respective terms in b. And so we can see that this factorization actually plays a key role in the marginalization in the sum product algorithm. Now an example here would be the joint probability of x1 to x5. We have seen in the previous lecture that in order to compute this marginal probability distribution, we have to marginalize over the random variable of x6, where we say that we will simply factorize out all the factors that does not contain x6 into the left side of the marginalization of the summation term over here. So we can collectively call all these factors that does not contain x6 as a, and this would become a multiplied by the conditional probability of x6 conditioned upon x2 and x5. So this would be similar to this term, and what we can do later would be to factorize out a into the left side of the summation term, and as a result we will get this over here, where we can simply apply the marginalization on this term and simply ignore the rest of the term that are on the left side. So this is according to the distributive law, and we have seen that this as a result leads to the sum product algorithm, which is extremely useful for us to compute all the marginal probability or conditional probabilities over all nodes without recomputing the messages. Now what's interesting here is that we can see that the distributive law applies to the max operator as well. So suppose that we are given a task of finding the max over these different terms over here, which consists of a multiplied by b1, a multiplied by b2, all the way until a multiplied by bn respectively. And we can see that this max operator, the maximization over these terms over here, is simply equivalent to the factorization of a and multiply by the maximization over the respective terms in b over b1 all the way to bn respectively. And what this means is that we can simply turn the elimination algorithm or the marginalization algorithm into a MAP elimination algorithm by simply replacing the sum operator with the max operator. And here's an example. Suppose that we are going to look at the max over x6, the random variable x6, in the joint over the joint probability of x1 all the way to x6. We can see that this is equivalent to maximization over x6, the random variable x6, and over the joint probability distribution factorized in this term as given by the Bayesian network that we have seen in the previous lecture. And similar to the summation term, where we have seen earlier in the previous slide, the example where it's a summation over x6. So since we say that the distributive law applies to both summation as well as maximization, what this means is that we can also simply push in the max operator into those terms that consist of x6 only. And in this case here, it would be this conditional probability of x6 conditional upon x2 and x5. And hence, all the other terms over here can be simply factorized out into the left side of the max operator term, because these are independent of x6. So here's a pseudocode of the map elimination algorithm, which is actually very similar to the variable elimination algorithm, and this allows us to find the maximal probability over x1 all the way to xn of a joint probability distribution of x1 all the way to xn. And the next thing that we do here would be to add each of the conditional probability into the active list, as well as the evidence potentials or evidence nodes into the active list. So these two steps here, these steps here are the same as the variable elimination algorithm. Then this is followed by the update step. So for each one of the random variable that we have placed in the ordering list of I, we will find all the potentials from the active list and start to do the start to apply the maximization operator, the max operator on these potential terms. So this is the only difference between the map elimination algorithm and the variable elimination algorithm. Other than the choice of the ordering doesn't matter anymore, because we don't have to place the query node at the last. There's no such notion of the query node in the map elimination algorithm. So here, the difference here would be, instead of a sum, we are doing a max over the random variable in the ordering list. And finally, when we are done by exhausting all the terms in the active list, we can find the maximal probability value that is equals to the scalar value on the active list. Here's an example. Suppose that we are given this Bayesian network over here, which can be factorized into this joint probability distribution over here. We choose an elimination order of 6, 5, 4, 3, 2, 1, for example. And in this case here, we further assume that the random variable x6 here is observed, where it's kept fixed at x6 bar over here, which we denote as the joint probability distribution conditioned upon x6 bar over here. And we are going to take the max over x1 all the way to x5 over here, since we have already observed x6. And this can be rewritten as max over the individual respective term of x1 all the way to x6, following the marginalization trick notation of using the delta x6 over here. And following the map elimination algorithm, we can simply do the maximization over all the random variable as following this particular elimination order. So in this case here, we will first start by eliminating x6 over here. So we will do a maximization over x6, and in all the potential list, in the active list which contains all these terms over here, we will follow the map elimination algorithm, the pseudocode given earlier, where we will simply look at the active list and find all the terms that consist of x6. And these are the two terms, so we will do a maximization over x6. So we can see that this is equivalent to this step over here, that we are pushing x6 into the factorization terms over here. And here we will compute m6 or max, and we are left with x2 and x5. Then we'll pass this message to the back into the active list. And the next thing that we will do, it would be to do a maximization over the random variable x5. And we'll look at the active list to get the terms that consist of x5 over here. And in this case, it would be p x5 conditional upon x3, as well as the message that we have computed earlier. So this we will take the max of x5 over these two terms over here, and that will give us a message of m5 max x2 and x3 over here. And then we will pass this back into the active list and continue the process until we exhaust all the terms in the active list, and we will be done with the maximization over the joint probability distribution. So let's look at the more detail on how the computation is actually done. When we talk about the maximization over the random variable x6, where x6 is actually a observed random variable, it's observed as x bar of 6, we can see that this is equivalent. This is the same as taking the slices of the conditional probability of x6 conditional upon x2 and x5 over here, where assuming that each one of the random variable takes two states over here, and we observe that x6 bar takes a state of 1, for example. So what we are interested in is that we are interested in all the entries, all the rows in this particular conditional probability tables, such that x6 takes a state of 1, and we'll form a new probability table over here, which denotes the message of x6 over here, where we simply observe x6 to be taking a state of 1. And in the next step of the maximization over x5, we simply pass the message of x6, m6 over here, which we have computed in the earlier step, as well as the conditional probability of x5 conditional upon x3 in this case over here. So we will look at these two tables to compute this maximization over x5. And what this maximization means is that, so the maximization over x5 over here, over the conditional probability of x5 conditional upon x3, and the message of m6 max over x2 and x5 can be expanded out into this form over here, where we simply write the max operator over the term of p of x5 taking a state of 0 condition upon x3 multiplied by m6 max over x2 and x5 equals to 0. And the next term would be the probability of x5 equals to 1. Now we're assuming that each random variable takes a binary state over x3 multiplied by m6 max x2 x5 equals to 1 over here. So what this means is that we're going to choose the max over x5, means that we're going to choose over these two possibilities. In the case where each random variable x takes k state, then we will have k possible choices. In this case, since we only have two states, then we will only have two choices over here, and we are going to take the one that gives rise to the maximal probability or the maximal value over here. And we are going to do this over all the combinations of x3 and x2, since these are the two random variables in the two product terms over here. So we are going to do this. Suppose that now we are going to look at x2 and x3. It's at the state of 0 and 0. We can actually fill this in to be 0 over here, as well as x2 to be 0 over here. And this term over here is 0, as well as this term over 0. So we can simply look at the table for this particular value when the conditional probability of x5 equals to 0, conditional upon x3 equals to 0, which we'll look at this table over here, corresponds to this term over here, b1. So here we can simply rewrite this term as b1 over here, in this case over here, when x2 and x3 equals to 0. So in this case here, and x5 equals to 0. In this case, we will look at this entry here where x3 and x5 both equals to 0, which is given by b1, which represents this conditional probability over here. And we will also look at the next term of m6, x2 and x5 both equals to 0. So this corresponds to this particular term over here, which is v1. So the first entry here would be b1 multiplied by v1. And the second entry over here would be at the state where x3 equals to 0 and x5 equals to 1. And that would be this term over here, which is given by b2. So we'll put b2 here, and then we'll multiply this by the message of m6 at the state of where x2 equals to 0 and x5 equals to 1, and that would be simply v3 over here. So we'll get these two terms over here. And now the maximization operator of over x5 simply means that I'm going to choose the maximum of these two, between these two, and write the value. Now suppose that b1 v1 gives the maximum value, then this would be equals to b1 v1, for example. Okay. And we'll do this over all the combinations of x2 and x3. So suppose that x2 and x3 both now equals to 1. We'll simply evaluate these terms here. Now x3 will be equals to 1, and x2 will be equals to 1. And x3 here will be equals to 1, as well as x2 here will now also be equals to 1. And we will simply look up the two tables over here to find the corresponding entries and evaluate the maximum term between the two product terms over here. And the maximum one will be the entry in this table over here. So what this means is that in this case over here, since we are doing a maximization over x5, the resulting table would be in the order of the remaining variable in the message, which is x2 and x3. So in the case where we have a binary random variable, this means that the resulting size of the table of m5 over here would be simply equals to 4. In the case where we have k state, this would be the size of this table would be the k to the power of 2. Now one problem that we can observe in the max product algorithm that we have seen earlier would be a underflow problem, because we can see here is that we are forever multiplying two probabilities together. So after I have gotten the probabilities over here, I will, in the next step of the maximization, I will take the product of the two probabilities, and this will continue. This particular multiplication will continue for every one of the message that I am computing. So what happens here is that when we multiply two numbers, since this is a probability value, it has to be between 0 and 1. So what it means is that when I multiply two numbers that are between 0 and 1, suppose I multiply 0.33 to 0.12, for example, this number is going to get smaller and smaller as I do the multiplication. And this will lead to what we call the underflow problem, because as the number gets very small, 0.00000 something over here, my computer will not be able to represent this kind of or this level of precision, and this will lead to an underflow problem where everything will be represented by 0 in the end. So as a result, we will not be able to compute the max probability over this due to the underflow problem. And fortunately, this can be overcome by using the logarithm over all the probabilities. So what this means is that, what's interesting over here is that the distributive law still holds after we have applied the logarithm. And in this case, we can see that instead of a multiplied by b1, since we are taking the log of a and b, this would be equivalent to the log of a plus the log of b1 over here, which we simply denote as this operation, the sum operation over here. And we can see taking a max over this is equivalent to a plus the max over all the b's. And since we have taken a logarithm over here, the product of logarithm, because we are taking a logarithm, that means that a very small number over here would be represented by a sufficiently large number, and taking a product over two log terms which are sufficiently large, it does not have to be in the range of 0 to 1. This means that we will not face the underflow problem anymore. And as a result, we have turned the max product algorithm into a max sum algorithm over here. So because instead of the product, we have now we are using the logarithm to convert the product into a summation as shown in this step over here. And we can see that interestingly, the underflow problem, it does not occur or it does not exist in the marginalization or the sum product algorithm. The reason is because instead of taking a max over the probability values over here, in this case here, the maximum simply means that I'm choosing one of the out of the two product terms over here. I'm not doing any other operation over here anymore. And by taking another max over this, it will still be a product of another probability value. So I'm forever taking the product of probability values, and this will lead to a very small value or the underflow problem. But in the case of the marginalization, I'll be actually summing up these two probability values over here. So this means that the summation over here, it will turn a sufficiently small numbers over here into a larger number. And by doing this recursively, the summation over here, I'm still able to maintain the range of 0 to 1 without facing the underflow problem in the maximal probability case. Now we can see that the map elimination algorithm might not work over any general form of the graphical model. Here's an example where if we were to suppose that we were to take a max over a random variable of xi, for example, and in the factorized term over here, it happens that this factorization consists of many terms or a large elimination clique or a large clique over xi, for example. So this might be over a random variable of x1, x2, all the way to xm, where m here is a very large number. We can see that this is not going to work out well because in this case here, we'll still end up having a need to go through every one of these random variable, which is equivalent to a large elimination clique, as we have seen in the variable elimination algorithm. So similar to the variable elimination and the sum product algorithm, we'll see that the operation over here would always be efficient or will always be tractable on a tree. So we'll now look at the max product algorithm for a tree that represents the joint probability distribution. We can choose, similar to the sum product algorithm, we'll choose any node xf as the root of the tree, and the message passings are propagated inward from the leaves towards the root node. So here the message is defined as from a random variable xj towards xi over here. We will define this message as mji, and this message is over the max of ji over here, and this is equal to the max over ji over all the potentials, the unary potentials of xj as well as the binary potentials of xj and multiply by all the messages that are coming into the random variable node of xj over here. And once we are at the root node, we'll simply collect all the messages that are coming into the root node, denoted by m of ef over here. And we'll simply take the product of all these messages, multiply by the unary potential of the random variable of the root node over here, xf, and we'll do a maximization over the random variable of f over here. And as a result, I would be able to get the maximal probability over the joint distribution of x over here. So one question here is that in the case of the sum product algorithm, we do message passing all the way to the root node, and then we will do a downward pass from the root node to the leaf nodes to compute all the messages of the tree structure. And the question is that, do we also need to pass the messages back to the leaves for the max product algorithm? The answer is actually no. So in the case of the sum product algorithm, suppose that we have a tree over here, we are going to compute all the messages. The reason is because we are going to reuse these messages for all the individual marginal probability over all these random variables in the joint distribution. So hence, we need to compute all the messages in both directions in the sum product algorithm. But in this case, where we are computing the max product algorithm for trees, we realize that regardless of whatever choice that we made for the root node, whichever random variable in the joint distribution that we choose for the root node, the resulting maximal probability that we get over here will always be the same. This is, I will not go through a rigorous proof on this, but intuition here is that if you recall the example that I gave earlier, a two random variable x1 and x2, so the joint probability distribution here, x1, x2, is always going to be fixed over this two random variable over all the states over here. So regardless of whichever random variable that I choose as a node, after doing this maximization process over all the random variables, what I will get as a result would be the maximal probability that corresponds to the certain configuration of x1, x2 in the joint distribution. And this is clearly independent of the choice of the elimination or the choice of the maximization over all the orderings of the random variable, because the maximal probability is still going to be the same regardless of whichever order that I have chosen. So as a result, what I don't need to do here would be to pass the message downwards, because I'm not going to reuse the message anyways. I just need to randomly select a root node out of all the random variable in this joint probability distribution and pass all the messages upward towards this root node, and I'm done here, because as a result I will be able to get the maximal probability here. So once we have computed the maximal probability, the next problem that we have defined earlier would be to find the configuration of all the random variable such that we achieve the maximal joint probability distribution. And we'll make use of the messages to the root node from the sum product algorithm to compute this. So the question is that can this be simply done by an outward pass of the messages from the root to the leaf nodes so that we can find the configuration of all x? So in the case where we can see that just in the previous example where we have all the messages that we pass upward from the leaf nodes towards the root nodes over here. So since we have also computed for every message over here, we have computed a certain configuration of the random variable that maximizes the probability over here. So in this case, let's say this is x1, this is x2. I'm going to compute the max over x1 and the conditional probability of x2 and x1, for example, in this case over here. And then I'm going to proceed upward. So since I have already computed the maximal probability here, does that mean that I will just simply need to do a downward pass to track or to check all the configuration of this random variable that locally gives rise to the maximal probability? The answer to this is that no, we cannot simply just do a downward pass. Instead, we have to track a path of that gives rise to the maximal probability. We'll see why is this so. Now suppose that I have a chain structure, a chain graphical, undirected graphical model given by this figure over here. We can see that we can represent all the states of each random variable using what we call the lattice or trellis diagram. So here, each one of this square over here, this is not a graphical model, but each one of this square over here represents all the possible states of the random variable xn minus 2, for example. So in this case, each one of these random variable will take 3 states, 1, 2, or 3. So in this case here, there are actually 2 configurations that gives rise to the maximal probability. This is one of them, and this is another one of the configuration. And we can see that if we suppose that if we choose this guy over here as the root node, for example, and by doing a forward passing of the messages from xn minus 2 all the way to xn plus 1, we would have computed all the maximum. We will have all the maximum value of this random variable at each one of the max operation that we have done in the max product algorithm. And in the case where we have reached the root node, if we were to do a backward tracing, or if we were to do a downward passing back to the leaf node, what we could end up with in choosing the configuration would be the case where here, because there are 2 configurations that gives rise to the same value. So what this essentially means is that suppose that I'm able to view this graph with xn minus 2 all the way to xn plus 1. So this is the joint probability of xn minus 2 all the way to xn plus 1. And there are actually 2 peaks over here that gives rise to the same value, the same maximal probability value. And these 2 peaks corresponds to the configuration of these 2 sets of configuration over here. But if I were to do a downward pass, this means that I simply would end up choosing any one of these at any stage of the downward pass. And this means that I might not be consistent, because a correct solution would be this particular configuration over here that gives rise to one of the maximal value, for example, and the other configuration would give another maximal value of the joint probability distribution. But if I forget, if I don't trace the path, or I don't track the path and consider each one of these steps individually in the downward path, what happened here would be I might end up choosing that k equals to 2 for n plus 1, the random variable of n plus 1. And if I go back to this xn over here, I might end up choosing k equals to 3, because in this case here, there are actually 2 values that gives rise to the maximal probability. I might actually choose this, and then in the next step, I might actually end up choosing this again, for example. So in this case here, the configuration that of the random variables that gives rise to the maximal probability value is not consistent, because we can see that there are 2 sets of consistent values or states of all the random variables that gives rise to these 2 maximal values over here. So the solution here would be easy. We will simply record the maximization values, or the paths that we have seen, these paths that we have seen earlier on. So when we decide the next step over here, we need to consider the previous step, the path towards the previous step. And what we will end up with would be to trace the path that gives rise to a maximal configuration, to make sure that the configuration of the random variables that gives rise to that particular maximum value, it's consistent. And we'll do this by introducing another values over here, which we call delta ji, that records the configuration of xj. For example, when I'm moving from xj into xi, in this particular case over here, I'm going to record this value that achieves the maximum value. We'll see exactly how this is done. But before that, having defined this delta j of I during the inward pass, we'll be able to make use of this, because what happened here is that in the trellis diagram that I have seen earlier, so what happened is that in the inward pass, suppose this is my root node. In the inward pass, I will trace every one of these configuration when I get from the leaf node to the root node. Now suppose that there are 2 different values, or there are 2 different configurations that gives rise to the maximum value. I'll actually trace all these paths when I do the forward pass from the leaf node to the root node. And in the backward pass, in the downward pass from the root node to the leaf nodes, what I simply need to do would be to choose a maximal configuration at the root node. Now suppose that I'm going to choose k equals to 0 over here, because I noticed that once I reach the root node, there are two configurations of this root node that gives rise to the maximum value at k equals to 0 and k equals to 1, for example. And then what I will do here is that I can choose one of these value and start to trace the path backward into the leaf nodes by simply following what is recorded in delta ji over here. So what it also means is that I can actually exhaustively track all the paths and check all the configurations that gives rise to the maximal value over here. And here's the max product algorithm, where we do an upward pass and a downward pass by collecting all the messages that contains delta ji over here. So in this case here, the difference between this max product algorithm and what we have seen earlier would be that we have store all the paths that gives rise to the maximal probability, and we will add the outward pass that gives us the maximal, that tracks the path that of the maximal probability that I have described earlier. Now let's look at a more concrete example of to understand the pseudocode in the previous slide. Now suppose that we have a simple example over here, which is consists of three random variables x1, x2, and x3 over here. Now what I'm interested in would be to find the configuration of x1, x2, and x3 that gives rise to the maximal probability in this joint probability distribution over here. I'll do the same thing. I'll first start from the leaf nodes. Let's say if I choose x2 as my root nodes over here, I will first start to propagate the message from the leaf nodes of x1 and x3 respectively. So this is easy. I will simply do the same thing over here, where now suppose that my joint probability distribution over here, this guy over here, is given by simply the unary potential of x1 multiplied by the unary potential of x2 multiplied by the binary potential of x1 and x2 and the binary potential of x2 and x3. So this is what I have defined in this example over here. So a max over x1, this message over here, would simply apply a max over x1, a max over x1 on this joint probability distribution, and I need to pick out from the active list of the terms that consist of x1, and in this case would be phi of x1 and phi of x1, x2 over here. So I will need to do the maximization over these terms over here, and I'll follow the steps that I have explained earlier, where this max over x1 would be simply evaluated over, because there's another random variable here which is x2. So the resulting message over here would be m of 1 and the max over x2. Since I'm going to eliminate away x1, I will be left with x2, and the table would be assuming a binary random variable, the table would consist of 2 entries over here. So what happens here would be that I am going to evaluate this over the state of 0, and I can rewrite this into x2 equals to 0, and this max over x1 can be evaluated in this term over here, where I'm simply choosing the maximum over these two product terms, where x1 equals to 0 and x1 equals to 1 respectively. Now suppose that these two terms are a1 and a2 respectively, and further supposing that a1 is the bigger term out of these two, I'm going to select a1, for example. So in this case over here, we can actually visualize this in a trellis diagram. So suppose that these two states over here represents the two possible states of x1, and these two states over here represent the possible state of x2. So the choice of the multiplication or the multiplication of these two potential terms over the two different states of x1 over here. Condition subjected to the that x2 is held at 0, a state of 0 over here. So we are looking at this x2 at 0 over here in this entry over here. So what happens here is that since x1 can take two possible states, these are the two paths that we are looking at over here, and where x1 simply takes 0 or 1 over here. So we are choosing between these two values of a1 and a2 respectively. So in this case here, we are choosing a1 to be the maximal term. So here I'm going to denote this as the red line over here that denotes the maximum term over here. So in this case, I'm going to record this path. I'm going to record this particular path where for x2 equals to 0, the maximization of this over x1 is actually at the state of x1 equals to 0, which is this term over here. So I'm going to, in other words, I'm actually recording this path, which I recorded as x1 max equals to 0 and x2 equals to 0. So similarly, I'm going to do this for x2 at 1, at the state of 1 over here. And what this means is that what this corresponds to in the trellis diagram would be this guy over here. And I can see that as a result of the expansion of the max operator, I will end up with a3 and a4, which corresponds to the state of x1 equals to 0 and 1 respectively, a3 and a4. And suppose that a4 is the larger number between the two. So this means that I'm actually selecting these paths over here to give rise to a maximal value, the max over x1. And I'm going to record this path over here as x1 max is equals to the state of 1 when x2 is 1 over here. So similarly, I'm going to do it the same step in the other way over x3 as the leaf nodes over here. So this results in the potential maximization of x3 over the unary potential of x3 and the binary potential of x3 and x2 over here. And I'm going to evaluate, since the maximization means that I'm going to remove x3, so I'm going to evaluate this term over x2 equals to 0. So what this means is that I'm going to look at this term over here where x2 equals to 0, and I'm going to consider this between the states of x3 equals to 0 and x3 equals to 3. So these two terms here, I'm going to look at it, which corresponds to b1 and b3 respectively. So I'm going to choose, suppose that b3 is the maximal value out of these two terms over here. I'm going to what I'm going to do would be to record this particular path in the maximization step over here. So I'm going to say that at the state of x2 equals to 0, the value of x3 that gives rise to the maximal value would be equals to 1, which corresponds to this value over here. And similarly, I'm going to evaluate this term over the x2, the state of x2 equals to 1 over here. And here, I'm going to evaluate over the state of x3 equals to 0 and x3 equals to 1, which corresponds to b2 and b4 over here. Now suppose that b2 is the highest value. I'm going to track these paths in my table over here, and I'm going to record this as delta 32x3, where x3 maximum is 0, and at the state where x2 equals to 1. So now finally, when I'm at the root node, all I need to do would be the maximization over the root node over the product of all the individual message that is passed from x1 and x3 respectively into x2, as well as the unary potential of x2 over here. And what this means is that I'm going to evaluate this term over x2 equals to 0, as well as x2 equals to 1. And this means that I'm looking at this term over here in the trellis diagram when x2 equals to 0. So here, what I'm looking at would be the multiplication of a1 with a3 and the unary potential of x2 equals to 0 over here. And I'm going to choose whether this is the larger value, which I finally denote as D1 over here, or the value is larger from this multiplication over here of A4 and B1 multiplied by the unary potential of x2 equals to 1 over here, which I denote as D2. Now suppose that D1 and D2 are the same value. We will get, what this means is that we will get two configurations of the random variable x1, x2, and x3 that gives rise to the same probability, the same maximal probability value. And we can see that by doing the downward pass over here, we simply need to go the other direction over here. We can trace out for every one of these configuration over here. We can trace out what is the maximal configuration of the random variable that gives rise to the maximal probability. Now suppose that if I were to choose the configuration at x2 equals to 0, for example, the downward pass here would be, I'm choosing this x2 equals to 0, so the downward pass into x1, I can easily track which state of the x1 gives rise to the maximal probability when x2 equals to 0 over here. So in this case, it's x1 equals to 0, which corresponds to this path over here. And when I'm passing the downward message from x2 to x3, what happens here is that I can also look at the configuration over here where x2 equals to 0. I can see that the configuration of x3 that gives rise to the maximal probability is when x3 equals to 1 in the table over here. So this would correspond to this path. So similarly, if I using the configuration when x2 equals to 1, we can trace back into x1 and x3, the leaf nodes here, to find out the maximal configuration. So here we're looking at x2 equals to 1. We can see that the maximal configuration is actually x1 equals to 1, which corresponds to this path over here. And similarly for x3, when x2 equals to 1, we can see that the maximal configuration is x3 equals to 0, which corresponds to this path over here. Hence, as a result, we'll be able to get the maximal configuration that gives rise to the maximal probability of this joint distribution of x1, 2, and 3.